the rigid rod arrangement. So imagine a rigid rod of uniform density, length L, mass M. We proved quite extensively that the moment of inertia about its center is 1/12 ml squared. The thing is, calculating moments of inertia is laborious. It takes a lot of time and is mathematically deep and heavy. There are shortcuts. And so one of those shortcuts is the parallel axis theorem. The parallel axis theorem allows you to shift the moment of inertia to another location without having to do any more calculus, without having to start the problem over again, without having to integrate or anything. It just allows you to shift it. But you have to be very careful. It is called the parallel axis theorem on purpose. So this theorem will allow you to shift the axis as long as it's parallel to the one you're given. So the way it works is this. The parallel axis, the moment of inertia along a parallel axis, is equal to the moment of inertia about the center of mass plus how much you shift it. This is the shift portion. So if you want to find a different moment of inertia, if you want to spin a meter stick about a different axis, you don't have to calculate the moment of inertia directly as long as the axis you want to shift it to is parallel to the one you know. Now, I want to be really careful here because I found out earlier in the week that the word parallel may not be something all of you understand. So let's take a look at a picture for a minute. Everybody understand what I'm asking for? Because I'm going to come by and check your paper, and when you don't have it, I'm probably going to say something snarky or mean or whatever I have available at the moment. So parallel axis theorem to find the moment of inertia of a disk about its edge. That we did successfully use it to find its 3/2 mr squared. Yay. I want to show you something else using the parallel axis theorem. This is a little harder to walk down. It's going to be a more difficult challenge for you, but it has to do with composite objects. A composite object is when you take and create the moment of inertia by putting some things together that maybe look like or mimic something. Like over there in a bit, I want to use the compositing of an object to recreate what we have set up as our demonstration. I've got a rigid rod right here, fixated at its center, but I have these objects over here which are square pieces of metal, with some kind of odd funky shape on top of it. How important is it that I know the moment of inertia of this object in order to be able to determine the whole moment of inertia here? And so what I need you to kind of see, and this might not be easy, so I want to be really clear, is once we start shifting the axis, you notice the moment of inertia is increasing. And you see that already, right? We went from 1/2 to 3/2, because we're pushing more of the weight further away from the axis of rotation. And the more we do that, the more exaggerated it gets. So I want to compare the moment of inertia of a square about its middle, and then take that square and move it over 24 centimeters and see the change in the moment of inertia. Does that make sense? So the moment of inertia of a rectangular shaped object is, I have forgotten it. I'm feeling the same way. I could look it up, but that sounds like quitter talk to me. So, being that we are smartsy people, you don't have to do it, but I think I can. So I'm going to try. I'm not going to talk while I'm doing it, because that way you might like bury your head over there and try it yourself. I believe in you. Well, I believe in some of you. I have cause to believe in many of you, but we'll see. I am choosing the axis of rotation to be at its center. This is a square-ish looking thing. So I'm going to call this, width W, and this length L. I'm going to choose a piece of the object here and call that my DM. Oh, wait, I said I wasn't going to say all this out loud. I'm going to keep going anyways. I'm going to point to it by using rectangular coordinates. So that means I'm going to go out a distance X and up a distance Y. And that'll point to that object. I think I can point to every object by going from negative W over 2 to positive W over 2, and from negative L over 2 to positive L over 2. That seems reasonable. I might just find one square in the upper right-hand corner and multiply by 4. That would do it too. So going 0 to W over 2 and 0 to L over 2. Does anybody following this argument or not caring? I'm just talking it out because this is not an unreasonable thing for me to put on your test if you catch my meaning. So let's see. I have set up what my DM is. I'm going to say that this little distance is dy and this little distance is dx, and my area will be dx dy. That looks good. The entire mass is m, and the entire area is L times W. Okay, so I set up my mass per area, and I'm going to set this equal to dm over dA, but I'm going to replace dA with dx times dy. I'm going to solve this for dm and get dm equals m over L times W dx dy. I think I've done all of the steps necessary to set up and establish my integral. So now let's get my integral started. I equals the integral of r squared dm. This is where you run into trouble. So buck up, pilgrims. We might have troubles here. What's my perpendicular distance? I'm pretty sure my perpendicular distance is going to have to be x squared plus y squared to the 1/2 power. Right? Really? Wait. Somebody just said out loud they don't know what that is. It's the Pythagorean theorem. So those of you who just said, I don't know what it is, and yes, I heard you. X, Y, hypotenuse. So this will equal, this all has to now be squared because it's r squared. What? This is just our r right here, the perpendicular distance from the center. I'm sorry, Elizabeth, could you say that please just a tiny bit louder so somebody beyond the person sitting right next to you can hear, so I can correct whatever mistake I've made. So Anthony's asked where the 4 comes from. Please raise your hand if you know where the 4 came from. Okay, so it's not all of you. So several of you don't know where the 4 came from. It's not just Anthony. Okay, so I should be nice to Anthony for asking this question. When I set my limits, Anthony, instead of setting it from here to here and from here to here, I decided to set my limits so I could get a 0 in there from here to here and from here to here. That would only give me the moment of inertia of that section. But I get to finish. How many sections are there, Anthony? There are 4. So I was thinking that perhaps if we multiply our answer by 4, we would get the whole thing. Where did the 4 boxes come from? Did we all? All right. As fun as this is, and I'm really taking way longer for this than I was. I was only going to take a few minutes for this. I'm bringing this particular problem up. I have given you problems that I know are within our capabilities to do. I have some calculus people in the room, and some that may have finished BC, but this probably didn't make the curriculum. And part of the reason is because we can't split these up into a just one about X and just one about Y. So this is why this can't be on the test. Now, I don't know that you would have thought to do this anyways, even though we have talked about different things like this. But this problem, you understand, it's just another level above. And there are things we just can't do. I've shown you the ones that are in our capabilities, but we have a whole bunch that just aren't. Now, you will learn these things. And I should take a moment because I'm trying to make a point, and I know it doesn't feel that way. The moment of inertia of an object that is square is 1/2 m x squared plus y squared. This ends up being the answer. And it's just the x dimension times the y dimension, and you sum it up. If we're dealing with that thing over there, it is 3 centimeters on a side and has a mass of 280 grams. So if that's the square, then let's find its moment of inertia about its middle, all right? So again, we're going to have 1/2 times 0.28 times 0.03 squared plus 0.03 squared. This is its moment of inertia about its center of mass. You're just going to throw out a number. So I know this number is terribly small, but could somebody tell me what it is? I'll start with the 0.0, and there's many more to come. What do we got? I believe you. More. What's that? 258? 252. 252? All right. So about its middle, very small moment of inertia. We're going to shift it 24 centimeters to the side, which means we're going to take this moment of inertia and we're going to have the same mass, 0.28, but shifted to 0.24 centimeters squared. That's the shift distance, because that's where it is right now, 24 centimeters from the center. Could you calculate the new moment of inertia? Actually, do me just one big favor. Just tell me what this is. 0.24 squared times 0.28. 1/6 what? Three zeros, 1 0. So it's 2 orders of magnitude bigger than it was. Do you think adding this to this number is going to make much of a difference? Once you've shifted the axis outside the body of the object's shape doesn't really matter anymore. That's what this is telling you. So we don't have a specific time when this occurs, but when you look at the relationship between the parallel axis theorem and the center of mass, once this becomes bigger than the size of the object, this term takes over. In fact, if x is much bigger than the size of the object, then the moment of inertia just becomes mx squared. This is the point mass simplification. The moment of inertia of a point mass is just mx squared, or mr squared, if you want a more generic letter for it. Meaning when you are rotating an object outside of the body of the object, it is just a point mass. There's no specific point where that actually occurs. But I'd say once you start getting an order of magnitude larger, then you probably don't have to worry about the shape of the object anymore. I mean, the Earth is really big, and so is the moon. But when we talk about the moment of inertia of the Earth-Moon system, we just treat the Earth and Moon as point masses, because they're far enough apart where the point at which they rotate is outside the body of the Moon completely and nearly outside the Earth. And this is definitely true between the Sun-Earth system. For this, believe it or not, you don't really need to know that those are square. They're so far away from the center of rotation that you just treat them as a point mass. So as a general rule, when you're rotating something outside of its body, so if you have, say, a dumbbell, which would have, say, spherical edges or plates on the edge, if I'm rotating this about its center, even though these probably have some kind of moment of inertia at that particular range, I would just treat these as point masses and only worry about the bar portion as its shape, because its rotational axis is through its center. Again, that's how we use the parallel axis theorem. It has 2 parts to it: using it to actually shift the axis and using it in the extreme as the point mass formula. Good? Well, I've lost a little bit of time, and it's my own doing. When we first started our conversation about how to deal with the with moment of inertia, one of the things I did is we did a summation first, right? And we used the point mass formula to do the summation of the moment of inertia by doing a quick estimation, breaking an object up into individual pieces and adding those pieces up. And then from there we evolved to finding the moment of inertia using calculus, which had a process. Now I'm expecting you guys to be able to complete that process for any shape that you are given within reason. But your homework is going to specifically ask for you to repeat the moment of inertia of a rigid rod, the moment of inertia of a ring, and the moment of inertia of a disc. And then there might be 1 or 2 more on there that I'd like you to try. They're challenging. And for those of you who have that kind of analytical mind and would like the challenge, you should give them a solid attempt, especially if you have some confidence in your calculus skills. At the same time, though, I wanted to be forthright with you that don't be too concerned if you can't get to the answer. Following the process is what I want you to be able to do. Does that make sense? So don't spend hours on one of those, but do complete the process as far along as you can get it. When we did the moment of inertia of the rigid rod, we did it both about its end and about its middle. About its middle was 1/12 ml squared. And I've constructed a bit of a moment of inertia table on the board for you. And that's actually the first page of your new homework set. If I ever finish the last page, I'll go ahead and post it. That way you can provide me with your learning artifacts about how well you perform. It's not hard to calculate the moment of inertia about the end or the middle or any other place. We know that it's just setting our limits and choosing the appropriate limits for what's been put in front of us. But calculating a moment of inertia is a laborious task, and there are some shortcuts that have been given to help you find a moment of inertia more quickly. The one that I want to talk about today is the parallel axis theorem, which allows you to shift the axis to a different location within your object. There's some caveats, and they're pretty big ones. So for the rigid rod, which is very one-dimensional, it's not going to seem like a big deal. But for other objects and other shapes, it can become a big deal pretty fast. So let's talk about how the parallel axis theorem works. It states that you can shift the moment of inertia to any parallel axis if you know the moment of inertia through the center of mass. You simply have to add a term that deals with the shift distance. X represents the shift distance. Of course, be aware you can solve for any one of the things that are here. So if you have the moment of inertia of an object about its edge and you want to shift it to the middle, you could use this too, correct? So I could have started with the 1/3 and showed that we could shift it to the middle using this formula. But I've chosen to start with the 1/12 and show that we can shift it to the edge. We know what the answer is. It's on the board right now. It's 1/3 ml squared. So let's see how this particular thing works. We happen to know the center of mass of the, we happen to know the moment of inertia about the center of mass. So we'll plug that in as 1/12 ml squared. We're now going to use that to shift the axis to the end. So how far are we shifting it if we're shifting from here to here? L/2. Now this is just pretty straightforward algebra, isn't it? So 1/12 ml squared plus 1/4 ml squared. I'm thinking that you guys can add two fractions together. Perhaps maybe get common denominators first. Make that 3/12. And then I have 3/12 plus 1/12 is 4/12, which is 1/3. I mean, we kind of knew that was coming, but it's the parallel axis theorem. It's how it works. It's relatively straightforward and not particularly difficult to deal with. Parallel axis theorem is not a particularly challenging thing, but I do want to point out a couple of things about the parallel axis theorem that aren't obvious. Let's take a minute to just talk about an actual disk, something that we could measure, and I want to use this as a bit of a more than just an example. It's hard for me to impress this upon you. So, and I found I did not do a particularly good job in 6th period trying to make this happen. So, not challenging, right? It's just a number. It's a small number. I get that. So when you find it, did you do 0.03 times 0.05 squared all over 2? That's all I'm asking for. So I'm thinking it's 135, but with some zeros in front of it. Is that it, right? Because it's got to be, no, not 135, it's 25, 375. Half 75 is 37.5, so 375 with some zeros in front of it? How many zeros in front of it? 5 zeros in front of it? I'll believe 4. And that's kilograms, meters squared. So we're keeping it in our regular units. We could have left it grams, centimeters squared, but we're just going to do some comparisons. Now, that would be if I was to spin this about its center. But if I spin it about its center, I put it at the middle of this thing. What if instead I shift it over to the end, which is 24 centimeters from the center? And I go to spin this now. Can we find a new moment of inertia? We shifted it 24 centimeters off axis. So it's going to go around in a circle, but it's also going to be spinning as it goes around in that circle, right? So it's still, this moment of inertia still contributes. So again, we're going to place it on a beam that's going to shift it 24 centimeters from the axis of rotation. So we want to find the parallel, use the parallel axis theorem to find the new moment of inertia. And please do it like this. Just find the additional amount. Find the mx squared portion. We all good? Everybody got it? Just a calculator, right? Punching some buttons. So, we all done? I can call on anybody, right? And I'll be happy with their results. What you got, Hershey? So I can't call on just anybody. Can I call on Edward? .00, what was that? 1728 kilograms meters squared. Now, I'm seeing 2 zeros there and 4 zeros there. 3 orders of magnitude different, right? 2 orders of magnitude different. That's massive. I mean, if I add these two numbers together, if I go ahead and take this, put it over here and add it in, is it going to make a dent in this? I won't even see it till I get to the 3rd decimal place, right? So it'll change this number. That might not even be measurable. I'm bringing it up because the first thing I want to emphasize about this is the moment your axis of rotation starts to get outside the body of the object, it really is no longer about that object's shape. Right? We said that the moment of inertia is a measure of the inertia based on the shape of the object. But once the axis of rotation is outside, this term becomes much bigger than this term. Now, there's no point at which that happens. There's a point at which we can't tell the difference between it being a circle, that mass, or a square, that mass. We just moved it, what? This was a little bit more than a little bit less than 5 times the radius. The radius was 5 centimeters. We moved it 24. Do you think it'd be much different if it was just 2 times the radius? You understand, it really starts to get, it was a big shift when we went from the center to the edge, right? 3 times the moment of inertia. It was 1/2 and it shifted to 3/2. And that was still touching the object. You start getting outside the object and clearly this term takes over. The basic concept that I'm trying to instruct you on is that most objects, when rotated outside their body, can be treated as point masses. Their shape no longer matters. So the moment you start having an axis of rotation that is outside the body of the object, the shape of that object doesn't really impact the answer. Again, how do you write that? Well, if I was looking at, say, this particular one where I had a disk, so it's 1/2 mr squared plus mx squared, I'm thinking when x is bigger than r, that's when this starts to happen. Does it have to be much bigger than r? No, not really. It doesn't really have to be much bigger than r. It becomes pretty overwhelming at 1r. And all the way overwhelming once you get maybe 2r away. Now imagine what 2r would be, right? If I put a 2 in for r, then it's 4. I'm adding 4 mr squared to 1/2 mr squared. You see what I'm saying? The shape doesn't really play as much of a role when you start getting outside the object. Which brought me to wanting to find the moment of inertia of that apparatus, to calculate it. Not with the disk in place, but with these masses in place. But I was thinking, when they're out here, we certainly can treat them as point masses. They're far enough away from the center. Maybe. But I am noticing that this is a square, right? We don't have the moment of inertia of a square up there. We should probably find it. Seems like a homework question for you guys. Find the moment of inertia of a square. Here's where I ran into a problem. 6th period, I acted like I didn't know the moment of inertia of a square. Actually, I know the moment of inertia of a rectangle. And I acted like I did. I said, well, we could just find it. And then we got this tirade and it got harder. The truth is, I want you to try. I want you to try and come up with the moment of inertia of a square. Or better yet, maybe the moment of inertia of a rectangle, about its center. I'm going to tell you, I'm trapping you. I'm putting you into a trap. Can you follow the set of instructions as far as possible? You will see the trap eventually. But just try. With them, I talked it out, which turned into the absurd after a moment or two. With you guys, I'm going to talk it out. And we'll see if it turns to be as absurd. So I recognize that I need to give some parameters here. So how about we'll make this the width of this rectangle and this the length of the rectangle. That all good? I'm going to identify the center. So I'll put some coordinates here together to help me. Well, that didn't work out the way I thought it would. Let's try that again. Screw you. What's happening to me? What's happening? Make it stop. Fine. Fine. Stupid drawing software. All right, now we're back in business. Here we go. There, identified the center. Let's go back to saying that this is W and this is L. All right, I've identified my axis of rotation. My next step is to identify a piece of the mass. I'm going to identify this piece of the mass, a small little square located right there. I want to point to that piece of mass. So I will point to it, but I'm noticing, and I hope you do too, that this is squarish, right? I'm thinking Cartesian coordinates would probably be the right way to describe this object. So I send out my little arrow to there, and then I send out my little arrow to there. And I say, I can define that piece's location by stating I am a distance x and a distance y. Can I use x and y to describe every piece of this object all over it? Sure. I could set my x to go from negative L over 2 to positive L over 2, and I could set my y to go from negative W over 2 to positive W over 2. I probably won't do that. I would probably just go from 0 to L over 2 and from 0 to W over 2 and multiply by 4. Do you see why I'd have to multiply by 4? This became a point of contention when Anthony said, why are you multiplying by 4? And then somebody else said they couldn't see that there were 4 boxes there. But I see that there are at least 4 boxes here, 4 little boxes. Would you agree that this could be a box? And if I go from 0 to L over 2 and 0 to W over 2, that would be 1/4 of the whole box. So 4 of them would be all, and I would just multiply my answer by 4. Does that seem like not an unreasonable thing to do? All right, so good. This class maybe has a heads up on the other class. We'll find out in a moment, or you guys are just quieter about not, asking questions. That's possible too, but nobody can be as quiet as Elizabeth. So I will state that this looks to be a little bit more in the y direction, and this looks like a little bit more in the x direction. So I will state that my piece of mass, which has mass dm, has an area dA that equals dx times dy. That all look good? Excellent. I think we are pretty close to building our integral, but we do have to deal with the density of the object, right? We need to find a way of expressing the mass of the object in terms of its shape. So I said take the entire mass of the object and divide by the total shape of the object, which would be m divided by L times W. That would be the density of the object, right? The surface density or areal density of the object. I'm going to set this equal to dm over dA, but not dA, dx times dy. This is the mass per unit area of my piece. And what do I do next? What's that? Solve for dm. Excellent. I think I will. And I would treat myself to a cookie, but I ate all my cookies already. So I thank Gracie for giving me some Thin Mints. And now that they're gone, I am a sadder person for it. All right, back to work. I think we have enough information to assemble our integral now. And so we begin by saying I equals the integral of r squared dm. Here's your first roadblock. What's r? Has to be the perpendicular distance from the center to our piece of mass. I don't think that's drawn into our picture right now, is it? I would have to draw that into our picture if I want to get a visual of what it is. That would be the perpendicular distance. If I'm spinning, remember, I'm spinning it this way. So that would be my perpendicular distance. Square root of x squared plus y squared. Then squared. All righty. Square root of x squared plus y squared. Then square it. Got it. Still need my integral symbol out front. And still have my dm there. I think it's time to replace dm. Okie dokie. So I think I can just write this as x squared plus y squared. dm will be m over lw dx dy. The thing about being the king is that I get to decide when we talk about fun stuff and I get to decide when we stop. That's why it's king. So I'll pull out the constants. What will we do now, Libby, that I've pulled out the constants? You give us something. I will need two integrals, right? dx and dy. So I'll script that and I'll have to decide on my limits. Go ahead. I gave some suggestions on limits, didn't I? So just take one of the suggestions, it'll be fine. I offered two different observations. Can't do 0 to x. It has to be based on the shape that's here. Harishi, do you want to help her out or you want to let her flounder a little longer? What's that? You don't know the answer either? How big is the shape, guys? L and W. If I'm starting from here and I go to here, I could do that in the x direction. What would those two limits be? All right, so that'd be 0 to L over 2. If I start from here and go to here, in the y direction, what have I done? 0 to W over 2. Does that cover the whole thing? It just covers the whole thing about me putting a square up there and saying we could change limits. You guys don't remember any of that? Because I did talk about that, did I not? Did I draw a yellow square over the top of that and indicate that there are 4 squares and we could find it from 0 to the edge and then multiply by 4. That's why I am bothered, because you didn't listen to that part. So yeah, I'm just gonna put a 4 here. Now, I wish I could say that was the hard part. That is not the hard part. This is the trap that's been laid. If you could do all of that, that's already apparently way up here. But getting here, I think, is trouble. Do you see why it's trouble? Those of you who have been paying attention the last couple of days, especially those of you who have had calculus or are in calculus now, especially my BC folks, you should be looking at this and saying, this doesn't fit what you said would happen yesterday. Because if you remember what I said would happen yesterday, I said you'd be in a situation where you would be able to split the integral up into one part that is all about one of the variables and one part that's all about the other variable. Can we do that here? Can I get the x just with dx and the y just with dy? I can't. This is an integral where you will need a technique. And it's a double integral, so you'll need a special technique. I'm afraid to say this one is outside your capabilities. Should that stop you? So because you're supposed to be resourceful people and because they give you an integral table, you need to know what to do with an integral table. I have an integral table. Most calculus books do. Your job is to go find it on an integral table. I have found it. Do you know what an integral table looks like? Look on your third page of your equation sheet so you can see an integral table. It gives you a set of common derivatives and a set of common integrals. Basically, it provides you with the antiderivative for a group of integrals. You guys see it there? Now, if this were on your exam, they would provide this antiderivative. What I'm saying to you is, if you can make it to this point, don't let this be the thing that stops you. You understand what I mean? If you go to Google and type integrate, put x squared plus y squared, and then put dx space dy, it will spit out the answer. So use your resources, please.